All right, so so this last lecture is going to be about the hydrodynamics and relevance to condensed matter of transport in symmetry-broken phases. So I'm going to skip. This was going to be the fourth lecture, so we're going to skip the bit about diffusive and incoherent, what I call incoherent metals, and we'll go to this one because I think it follows better from what I've talked about so far. Okay. So very good. So we talked about how in strongly correlated materials you should worry about conservation laws, and for the late time behavior, everything else decays. So there's another circumstance where you have to add something to the late time dynamics, and that's when you have a spontaneously broken continuous symmetry. And there we have to add the Goldstone bosons to hydrodynamics. And so I'm going to talk about, time permitting, I'm going to talk about two cases. I'll talk about the spontaneous breaking of the U1 charge and internal symmetry. That leads to superfluidity. It's also very relevant for superconductors. And then we'll talk about spontaneous breaking of space-time symmetry of translations. And so an example of that would be a charge density wave, where you spontaneously form a profile, for example, for the charge. For example, it could be cosine qx. Okay. So let's do the U1 case first. And so I'm going to show how you should include these spontaneous symmetry breaking effects into transport into hydrodynamics. And so for the U1, what I'm going to talk about is in this paper, which is with Luca and other people. Okay. So the idea is the following. When you spontaneously break a symmetry, then the ground state, the vacuum, is not invariant under the symmetry anymore. And so there's a manifold of vacua. And the Goldstone boson is a coordinate on this manifold of vacua. It parameterizes the angle, for example, in the Mexican hat. You spontaneously break your U1. There's this circle, and the Goldstone boson parameterizes the values in this circle. And so so the symmetry acts non-linearly. So Goldstones transform non-linearly under the symmetry, the U1 symmetry that's broken. So phi, we'll just go to phi plus epsilon. It shifts. Okay, this is non-linear. It doesn't get multiplied, and that's just the fact that the symmetry generator has to move you around this vacuum manifold. So now the generator of the symmetry is the charge, the total charge. Well, Q, which is the integral of rho, is the generates the U1 symmetry. And so in particular, because this generates the symmetry, and this is how, and phi shifts under the symmetry, it follows that a Goldstone boson has a commutator with the charge density, which is just IH bar. Okay? So hopefully many of you might have seen this statement before. So the phase, the Goldstone boson as an operator in a symmetry broken phase is conjugate to the charge density. Okay? And that's really just because we can just think of rho as dd phi, essentially, right? It shifts the phase, and so it has this commutator. Is everyone happy with that? Well, so you have, originally you take the total charge, and then you take the integral out, and then you need locality to get that this has to be true pointwise. So there's an extra assumption here about that you have a local theory, so you can go to the densities. Oh, I'm sorry. Yes, this is IH bar delta x minus y. I'm sorry. So a linear transformation would be what? So psi, some charge field would transform like e to the I epsilon psi. So this is a linear map. This is not a linear map. It's an affine map. Okay. So now, this is really the definition of a Goldstone boson, I think, if you like. It's an operator that has this commutator with the density, the charge density. Okay, and again, all it means is that you have a manifold of vacua. The charge, the symmetry moves you, which is generated by the charge, the total charge, moves you around this circle, and the Goldstone boson tells you where you are on that circle. Okay. And we're going to see that this implies the existence of another light mode, which is going to be the Goldstone boson. Okay. So how do we do that? So the Hamiltonian. Let's see. How does the charge enter in the Hamiltonian? So the Hamiltonian, there's a chemical potential times the total charge. Right? So the chemical potential in equilibrium, and then there can be more terms. Right? But the energy cost of changing the chemical potential is defined as the energy cost of changing the charge. All right? So this is how the charge appears. And so now we can just combine this and this with essentially the equation of motion, and we're going to get that phi dot, right, which is up to some factors of I, and the signs that I'll surely get wrong, is h commutator phi, which is, if you be careful with the signs, is minus mu. Okay, and so this is called the Josephson relation. Okay, and so this is a, I should say this is true for the, I'm looking at the k equals 0. This is true when you integrate over all space. So these are the k equals 0 modes. So that tells you that. Well, that tells you this. Okay. That a time varying phase Goldstone boson is equivalent to a potential difference. Okay. Yeah. So if I have a plate, two plates, and the phase takes different values here, and so there's a right, and so if this phase starts changing linearly in time, it will create a voltage difference between these two plates. Okay. But this then is telling you that now, if imagine we start fluctuating away from equilibrium, that there's going to be a connection between fluctuations in the density, which cause fluctuations in the chemical potential, will also cause fluctuations in the Goldstone boson. So this Goldstone mode gets dragged into the hydrodynamics. Okay, it's coupled through this Josephson relation. So we need to include phi in the hydrodynamics. And that's great because we have one extra mode and we have one extra equation. Okay, so everything's gonna, we can calculate everything. Now, so again, because it's the total charge, the chemical potential couples to the total charge. Again, this is why this is this is about uniform statements. So with inhomogeneities, so with space dependence, where this now it can become a function of k or of x, you can have derivative corrections to this. So there's phi dot is minus mu plus, well, actually the leading term turns out to be this one, but is that right? Yeah. But it doesn't matter. So what I'll just write here is derivative times stuff. Okay. So in the same way that the constitutive relations have this derivative expansion, okay, phi dot also has a derivative expansion. And that's fine because when you integrate to get the total space, these terms will drop out. And so this Josephson relation only constrains the homogeneous parts of phi dot. It relates the homogeneous part of phi with mu, and that's because it's the total charge that couples to the chemical potential in the Hamiltonian. Okay. So phi of x, when we start fluctuating, phi of x and mu of x there can be high derivative corrections to here. Okay, but they're not going to be important for what I want to say today. Well, they are allowed, so they're there. So okay, sorry. It's analogous to how should I okay. So this relation has to hold at k equals 0. Okay, and so by continuity we're allowing at small k some k plus k squared corrections to this formula.
So I mean, it's impossible to derive a local variant of this jealous.
Correct. That's right.
And what's the problem if I can use just the phi at a certain point, and then I have a rho at a certain point, that is the function, and I have a local jealous relation. You mean that there can be different terms which also contribute?
Yes. So I think you should find that it's that you're free to add these derivative terms, and it will still work. So right, because yes, let me see. Yeah, it does look like that, doesn't it? So let's see. No, right. Because yes, so good. Yes, because this is the definition of the chemical potential. Terms of gradients of rho. There will be other terms here in the Hamiltonian that depend on gradients of rho, and those, right? So exactly, good. The point is that this is the universal part of the Hamiltonian. This is the definition of mu, but in terms that depend on derivatives, there can be more terms here that will depend on derivatives of rho, and these will be. I'm sorry. Yeah, exactly. This is really the definition of mu, if you like. Yes. Yes, there will be corrections here that will appear as corrections there. Yeah. Thanks. Yes?
What about the higher powers of square?
So again, this is just the definition. This is exact. Actually, this is non-linearly exact because this is a definition of mu. Yes, IQ equals 0. Yes. Is that okay? Any other questions? Yeah, these are good questions. Okay. So now, so it turns out that actually so I'm going to ignore these high derivative corrections. They're important. They lead to dissipative effects, but they're not going to show up today. So, okay, so let's see. So the first thing I want to show is the zeroth order effect of what this extra term does. Okay, and so let's see what that is. So the way that you really want is to take a gradient of this equation, and so then define. So the superfluid velocity u phi is defined to be the gradient of phi. Okay. For units, people often should put in some factors of a mass. So just in case anyone wants to connect this with things you might have seen before, I'm just going to set this m to 1. Okay. If you don't know what m is, all the better. Okay. All right. So I'm not going to. There's some factors of m, but I'm not going to put them in. Okay. So u phi is defined to be this. So now we take the gradient of this equation, and then we're going to get that u phi dot is equal to minus grad mu plus higher derivative terms. Okay, and now let's calculate the conductivity the same way that we did yesterday. So remember let's pretend, just to make life simpler, let me forget about momentum and heat and just focus on charge, just to make life easier. So remember, with charge we had the conservation equation. Actually, we're not even going to need this, but rho dot just give j 0, and then we had right, very good. the first thing we need to do is rederive the constitutive relation. So now we have J equals. Okay, so we have to find a constitutive relation. So that's what I want to. Yes, right. So so with this extra term. So with this field phi. Sorry, I jumped the gun here. There's one thing we have to do first. So phi appears in one other place, so it has this equation, but it also changes the free energy. So the free energy is whatever we had before, but if we're going to add a grad phi squared, and this coefficient here we call rho s. This is the definition of rho s, which is called the superfluid stiffness. Again, there might be some factors of m that you normally see in this formula. So let's see, why is that? Right. So we have a new hydrodynamic variable phi. Okay. Now the free energy, because phi transforms, has this nonlinear transformation under the symmetry. Okay. And actually, the free energy has to be invariant under the symmetry because the free energy doesn't know what the vacuum is, right? And so the free energy can only depend on gradients of phi. Okay, in order to be invariant under this symmetry. And so we have isotropy and so on. The first term that you can write down is this grad phi squared term. Okay, so there will be a grad phi squared term in the free energy, right, which is this. And this also shows up. Another way to say that is that the thermodynamic relation for dE, which was TdS plus mu d rho. Okay, these were the hydrodynamic densities. There's now a new term. So remember, for momentum we had v d pi, right? This term leads to a new contribution here, which is rho s. Okay, so this we can write as u phi squared. Remember, u phi is this superfluid velocity, and so now there's a new term here, which is rho s u phi d u phi. Okay, and this essentially just comes from taking d, okay, through some thermodynamic relations from this f. When you rederive the sort of first law dE, you get an extra contribution from u phi. Let me say one more time. So the free energy was a function of mu, t, and the velocity. Okay, and then when you have this superfluid, it's also a function of the superfluid velocity, u phi. Okay, but there's a new thermodynamic variable. Is the superfluid is the superfluid velocity, and because it appears in f, it appears in derivatives of f, and it will also then it turns out it appears in the first law like this. Yes. This, yeah. So we're about to set v to 0, but v or u would be, it's the normal velocity. It's what's conjugate. It's the source for the momentum. So at this point, exactly. So we have the three symmetries are not changed from before: energy, charge, momentum, and those have their three sources, which are temperature, chemical potential, and velocity. And now there's a new mode, which is this Goldstone boson, which has got nothing to do with momentum. Okay, so this is called a velocity, but it's not related to translations. Okay, it's related to this internal symmetry, and so there's a new thermodynamic variable, so this can depend on u phi. Okay, yes.
So in a standard superfluid, this is the normal fluid velocity?
So yeah, there's some question of how you define things, but indeed there are two velocities, and some combination of them is going to be the yes. This is very good. This is the thing conjugate to momentum, which is related to translations. Okay. Yes.
So like this phi is the orthoparameter phase, right?
No, phi is the phase. Sorry, the autoparameter phase. Yes. Yes.
Then since the energy, thermodynamic energy is unobservable, why should it depend on?
It doesn't. It depends on gradients of the phase. So that is a physical thing, as we'll come to. So you can yeah, the difference in the phase between two regions is observable. And it's related to this. Right, yes. Yeah, so that's why it's grad phi, not phi that appears here.
So, I think so. The Goldstone models, I should not think about them as particle stuff, and so maybe it's
There's no phi is just an operator.
Goldstone boson. I just accepted this.
Well, there's going to be a new collective mode that you can think of, but it as a well, there's going to be a new sound mode.
So it doesn't have it doesn't have K's, like it doesn't have many concept quantities.
No, that's right. Just one. There's going to be one new conserved quantity, but just one. Yeah. Right. So there's one new variable phi, but there's also one new equation, which is this one. Right. So let's forget about heat and momentum, for example. So before we had this equation and then the constitutive relation. Now we have a new variable, phi, but it satisfies it has a new equation, so everything's fine. Yes.
Just to make it clear, are we supposed to end up with lambda galactica fluid model, or are we supposed to end up with
Yes.
something
No,
else?
this will this is I'm going to add some more stuff to that, but this is very classical superfluid hydrodynamics that I'm doing at the moment. Yes. Yes.
Before you had another equation, an equation with a susceptibility, charge density equals susceptibility times certain.
Yes.
So you also have another equation.
It's a bit subtle for phi because grad phi is both the source and the response, so it doesn't work in quite the same way. But what is true is that this rho s is this thing is a susceptible. This rho s is the second derivative of the free energy with respect to rho s, or 1 over rho s is related to this quantity. Okay? So that's really the definition of rho s. Yes.
More conceptual question. Like when doing all of this, you're assuming that all the charge in the system is forming this sliding density wave. Right?
Well, I haven't mentioned density wave yet. Let's leave. With a bit of luck, I'll get to density waves. But I haven't mentioned density. This is an internal symmetry that's been broken, and not all the charge. So this is related. There are two. Yeah. There are four separate. There's temperature. There's charge. There's this Goldstone boson, and there's a velocity, and they're all there. Let's get to see. There's no sliding mode yet. That's for CDW. Or is there an analog of your question for here too? Is there an analog for this? No. So let's leave it. Come ask me later. Okay. Good. So now we're ready to calculate the right. So so this extra term. So if you remember last time, we had in rho. In J, the first term there was a rho, there was a charge density times velocity term in the constitutive relation. And remember, this followed from this positivity of entropy production argument, right? That we found we needed to add this. And remember that this term, and it had to be a rho there, and that was closely connected to this term in the energy. If you may or may not remember, but we did an argument we calculated S dot, and we found various terms. And in order to cancel a term that came from here, with this term, we had to have a rho v. Remember, this term was forced on us by entropy production. Okay, so now that there's this term in the thermodynamics, it turns out that you're forced to have a new contribution here, which is rho s times the superfluid velocity. Okay, so I'm saying this is a 0th order. There are no derivatives. Oh, I should say. So the hydrodynamic variable is not phi, it's really grad phi. Okay, so one should think of grad phi as 0th order in derivatives. Okay, that's because what you can in equilibrium, phi is not well defined, but you can have a grad phi. You can have a constant gradient of phi is something that you can have in equilibrium. So grad phi is the hydro variable. And so the same argument that we did yesterday morning, or actually maybe the day before, for entropy production, with this extra term, it turns out that you're forced in the constitutive relation for J to have this rho s u phi term. Okay? So and this is the supercurrent. All right? This tells you that a gradient of this phase creates an electric current. Okay? And that's the supercurrent. So if you have a net density and you move, that creates a current. But if you have a gradient of the Goldstone boson, also creates a current. Okay? And that's forced on you by a 3-line argument that I won't do. Okay? But it's the same as what we did before. And then there's some higher derivative terms. Okay, so now let's just forget about, we already talked about momentum, so let's not worry about momentum. Now we can calculate the conductivity. So J is, well, remember there was a minus sigma 0 grad mu plus more terms. So J is, this is, again, just, let's just break translations, then we don't have to worry about velocity. Yes? I'm sorry, say again? Say one more time. I just can't hear. It's not the. Yeah. No. When I said good, I just there are various conserved quantities. I just want to focus on the effect of this one, so I'm just going to not write down this one. Okay. The way to do that, no, it's not a rest frame. Let's just break translation. So just consider an inhomogeneous system, okay? It can be as dirty as you like, and then you break momentums, and this term will just be gone, but you'll still have charge conservation, energy conservation, and you can certainly break the U1 symmetry independently of whether translations are broken or not. So let's just go to a non-translation invariant state, and then there's just no velocity, and I don't have to worry about this term. Okay? But it's just for convenience, really. So here, so what I want to show you is that J, now I have this term, which is U phi, but U phi has this Josephson relation, this grad mu, so this becomes rho s, and this U phi, I'm going to write as grad mu over I omega, right? Because I omega is the dot, ddt gives you the I omega, so that's this, and then there's this term, which is sigma 0 grad mu. So this should be familiar from what we did yesterday now. I take this out overall. Grad mu is minus the electric field, so this is E sigma 0 plus rho s I over omega, and then we know that I over omega has to come with a pi times the delta function. Okay, and so now I get this formula for the conductivity, and again it's divergent, okay, at 0 frequency. But now, so this is the same as what we had yesterday, but remember yesterday there was a rho squared here. It came from this term, right? We had a conserved momentum led to a divergent conductivity, and now we see that this supercurrent also leads to a divergent conductivity, all right? And that's superconductivity, or better, superfluidity. Right, so hopefully, does that make sense? So I've done exactly the same steps that I did before yesterday. So remember, yesterday we had J was rho times the velocity, and then we had pi dot plus the divergence of tau, and we use this to derive that the conductivity was sigma 0 plus rho squared over m I over omega plus this delta function. And now the same argument, but using the superfluid velocity instead of the velocity, says that the conductivity diverges, but now it's this superfluid stiffness that is proportional to not the charge. If it's perfectly clean and there are no magnetic fields, I mean, of course, it was once you start perturbing the system, they'll behave very differently, but in terms of the conductivity, they look the same. That's right. So indeed, there are two ways to get an infinite conductivity. One is with conserved momentum, and the other one is with a superfluid velocity. All right? And so now let's write this. Let's connect with what we were saying yesterday in terms of the memory matrix. So yesterday, the infinite conductivity came from a conserved momentum, so P dot is 0. And this momentum overlaps with the current. Okay? So what's the conserved operator here? So the conserved operator here is the supercurrent, which is the gradient of the integral of the gradient of the phase. Okay, so this operator is also conserved, and it overlaps with the current. Okay, and so this is sort of a topological effect. Okay, that you can have. So actually, the best way to do this is to put the system on a torus, on a circle. Okay, and so if you have a circle, so phi, it's a phase, right? Phi is a phase, so it only goes from 0 to 2 pi. So if you have a winding of the phase around the torus, so or around the circle, I'm sorry. So phi winds. We'll have a torus in a minute. It's the circle. So if phi winds around the circle, then this j is not 0. Okay. But it can't any local perturbation can't relax phi because it's a winding number. Okay, so but on the other hand, this gradient does create a current through this relationship. Okay, so yeah, it's a bit subtle actually. So what I want to say is that in a superfluid, the conductivity diverges, and with translation invariance, the conductivity diverges because momentum is conserved. In a superfluid, the conductivity diverges because this supercurrent is conserved. Because you have this phase degree of freedom, you have this Goldstone boson, and you can wind it around your system, and that's topologically protected, and that's why this thing doesn't decay.
What about phase slips?
Yeah, we're coming there. Yeah, we're coming there. Yes.
Keep the current, considering not really like the volume integral that you guys are integral over some cross section.
Well, let's put it on a torus, actually. Yeah. So then it would. Sorry. Yes. Sorry. I'm sorry. Yeah. Well, so this is a vector and this is a vector too. So you can have supercurrent in the two different directions. So all of this is in Landau-Lifshitz and probably many other places. Okay. Well, most of this, at least. Now, indeed, so related to the phase slip. But the interesting thing now is, is there something analogous to the momentum? So remember, when you have, if you weakly break translations, then we relax momentum conservation, and that gave us this Drude peak. Okay, and so you could ask, can you relax the supercurrent in a similar? Is there something analogous? All right, and so that's what I want to start talking about. So, okay, so again, are there any more questions about Goldstone bosons and why they carry a current? All right, so the logic is like this. There's this Goldstone boson. Basically, from basic definitions of Goldstone bosons, its derivative is related to the chemical potential. Okay. Then this fact, combined with the fact that grad phi has to appear in a free energy, okay, those two facts together force this U phi term to appear in the constitutive relation from entry production. Okay, so so I just let me be clear. So the definition of a Goldstone implies the Josephson relation. The Goldstone has to appear, it costs energy to create the gradient, so there's a free energy term. which is U phi squared rho s. These two things taken together with positivity of entry production imply that this term has to appear in the constitutive relation for J, okay? And this then implies an infinite connectivity, all right? That's how it works. So now the motivation for what I'm about to tell you about came from an experiment from a few years ago. So I want to digress a little bit and tell you about metal-insulator transitions. Okay, so if you take a 2D thin film, cool it down to very low temperatures, what do you expect to find? Okay, so historically speaking, you could expect two things. One is there could be Anderson localization in 2D, okay, and then you expect to get an insulator. So the electrons could localize. So it's a 2D film. The electrons could localize, and then you get an insulator. Or they could pair, in which case you'll get a let's say superfluid, superconductor, superfluid, say superfluid. Okay, all right. And so what was expected is that as very good. And so these are two possibilities. Now consider, right, and this is what's seen. You get a lot of insulators, a lot of superfluids at low T.
Maybe both at the same time, but also.
No. So this here I mean the U1 symmetry is broken, and if the U1 symmetry is not broken, then the expectation was that the electrons are not paired, and they will. Well, I'm getting there. I'm getting there. Yeah. So okay. However, so what was done was to try to tune between the two with the magnetic field, right? So suppose you found, you've got a superfluid in I don't want to. There's a little parenthesis here about why you can really use the words superfluid and superconductor interchangeably in this context. And I don't have time to go into it. Okay, so I'm just going to use the words superfluid and superconductor as effectively meaning the same thing, and I don't want to talk about that. Okay, okay, but let me just call it a superfluid. So you add a magnetic field, and the magnetic field will compete with the superfluid. Okay, so as a function of magnetic field, what you might expect it to be is a superfluid insulator quantum phase transition as a function of the magnetic field. Eventually, the magnetic field kills the superfluid, gets a charged superfluid. Because eventually expelling the flux lines becomes too expensive. Okay? But however, and this is seen, and this was seen. However, what happens in many cases is that there's an intermediate region where you have a superfluid. So here the connectivity is infinite. Here the connectivity is 0. You often observe a metallic phase in the middle, okay, where the conductivity is finite. All right. This has been very controversial over a couple of decades, but I think this is observed. Yes.
So the experiments are always trying to define a temperature.
Well, of course, but
how do you know that for making lower temperature, eventually?
Right. Very good. I mean, right? Indeed. So in practice, so the arguments, people do scaling collapses as a function of temperature. Okay, and so in the earlier papers, that measurements that were interpreted as a superfluid to insulator transition, there's supposed to be a quantum critical point separating them, and various data can be collapsed as a function of temperature over, I guess, B minus B critical, okay, schematically. And they show a scaling form towards this point, all right? How this phase shows up is as this scaling just breaks down at some temperature, okay? So it at the very least suggests that there's not what had been previously interpreted as a quantum critical point separating the two is that breaks down at sufficiently low temperatures. It could be that there's yet another change at even lower temperatures, but anyway, I'm about to tell you why this is a very reasonable thing anyway. Okay. Yes, indeed, T equals 0 is you know, very cold. Yeah. Right. Okay, but it doesn't matter for all practice. Actually, in fact, good. I don't. There is a big theoretical debate about what can actually happen strictly at t equals 0. Okay, but this I mean a sort of for all practical purposes experimentally low temperatures. Okay. There's definitely at finite but low temperatures an interesting phase that intervenes between these two phases. Okay, and then so the starting point of this paper that I'm telling you about that we wrote was inspired by this measurement. So in the experimental paper is this one. This is by the group of Armitage and Johns Hopkins. And so he measured the optical conductivity, sigma of omega, across this diagram, all right? Across this phase diagram. And what he sees is that in the superfluid, of course, there's essentially a delta function in the conductivity. Of course, you don't see the delta function. What you see is the 1 over omega in the imaginary parts, right? So remember, it was I omega plus delta omega, okay? In the insulator, there's no peak. It's essentially flat, okay? And in this intermediate region, especially as you go close to the critical points, there's a very sharp Drude peak, all right? And furthermore, this time scale that appears here is very long. So the width is very short, and it's much shorter than any estimate that you would get of the electron lifetime, of the single particle lifetime. So what the data looks like is that this width is the lifetime of some long-lived collective mode, okay? And what is the natural collective mode? The natural collective mode is the supercurrents, okay? And so one would like to interpret this region here as a failed superfluid. Okay, so where the supercurrent is long-lived, but not infinitely long-lived. Okay, in the same way that what we were talking about yesterday, momentum was long-lived, but not infinitely long-lived. All right? Yes.
You have a magnetic field.
Yes.
Does it affect all the
Yes, that's right. So once parity is broken, all kinds of things can happen, but it depends on scales, and here I think the magnetic field its effect on transport are probably quite weak, and one reason for that is that at some point you might expect the peak to actually move, there'd be a cyclotron motion in the magnetic field, and the peak would actually move away from 0, actually, which can all be described. You can add magnetic fields to everything I'm saying, but we're going to assume that in this first pass that the only role of the magnetic field is to kill the superfluid, to weaken the superfluid, but it doesn't actually enter the hydro in an important way. But one can add it. It can be added. So there's a very nice thing. So let me tell you, so what relaxes the superfluid? Okay, so we know what relaxes momentum. It's disorder or a lattice. So let me tell you about what effects can degrade a supercurrent. Yes?
So basically you are in 2 dimensions at finite temperature. So in principle you cannot even break, you cannot really have a spontaneously broken phase. Does this work?
That's quite connected to what I'm. So BKT physics is going to be quite closely connected to what I'm going to talk about. But actually, it depends whether the vortices are unbound or not. So when the vortices are bound, this superfluid hydro is still correct, actually. Yeah. Sorry, is that what yeah. Okay, so very good. Okay, so what process? Remember, how do we look at P dot? So before we had the Hamiltonian, and there was a translationally invariant Hamiltonian, plus a weak perturbation that broke translations, and we found this by P dot was commutator of H with P, H prime, and that was not 0. Okay, so now we'd like to add something to the Hamiltonian that doesn't commute with this J phi. It's a bit subtle. Okay, the picture, the intuition is, well, what's happening is the following. So let's put up the system on a torus. spatial torus. So now let's talk about vortices. Okay, so basically the idea is this thing was conserved because there was a supercurrent, a winding number around here. And so now I'm going to show you that the only way to degrade, you have to fight topology with topology. Okay, so the only way to degrade a supercurrent is with a topological excitation. Okay, because anything that you do locally can't kill the winding. Right. So suppose you have no winding, but there's a condensate. So now you can create a vortex, and let's just put in very close together a vortex and an anti-vortex. So a vortex has a 2 pi phase as you wind around it. So let me draw lines of constant phase. Right. So the phase is 0, pi, so pi over 2, pi, 3 pi over 2. Right. That's the phase winding around. And then an anti-vortex also has a phase winding around in the other direction. And so I can connect these phase lines. I can connect these lines of constant phase. Right. And what in this picture, so this is very localized. So if I'm far away from the vortices here, if I move across here, the phase doesn't change. If I move across here, the phase doesn't change. But if I move through here, the phase jumps by 2 pi. Yes? Now I take these vortices, I move them apart, and I take them to the back of the torus, and I annihilate them again. Okay? So now, after this process of creation, pair annihilation, as you move them apart, the flux lines spread out, and then when you annihilate the winding spreads out, and then what you're left with at the end is just a 2 pi. There are no vortices left anymore, but you've created a 2 pi gradient. Okay? So by moving a pair of vortices around the sample, you can create a phase gradient. Similarly, if you start the phase gradient, you can move the vortices the other way around, and you can annihilate the phase gradient. Okay? And so now moving away from the torus, the idea is the following: if you set up, if there are some vortices in your system, and there are because there's a magnetic field, then you set up a phase gradient across your sample. That's a supercurrent. What will happen is the vortices will start moving across the sample, and every time a vortex moves across your sample, the phase gradient drops by 2 pi. And it's this process. Okay, and so this process you expect it to degrade your supercurrent. So we might expect, in terms of the hydro variables, u phi. So we had u phi dot was minus grad mu. We might expect some minus big omega u phi, some superfluid relaxation rate due to the rate at which vortices are pushed across the sample. Okay, sound reasonable? And so this is, and you might expect this to create a finite resistance. Okay, this is an old story. This is called flux. I may get the wrong words, but anyway, let's call it a flux flow resistance. Okay, and in fact, in 2 dimensions, when often at any finite temperature there are some vortices, and actually the conductivity is never infinite. The resistivity is never 0 in 2 dimensions because of these vortices. Even when you think you should have a superconductor, there's always this. So normally, if you plot the resistivity against temperature in 3D, you get something like this, where the resistivity just drops. Okay, so what you typically get in 2D is actually a decay like this, and that's because there are always these vortices that move across the sample. Okay, and so another way of saying it, these vortices are disordering the phase. Yes. Yeah, right. So let me see, 0 mag. So then it relates to this Kosterlitz-Thouless physics. So you have to be above some temperature. Right. Okay, so hopefully, so first let's do what we did yesterday. We did 2 things yesterday. So let's do the equivalent of the first thing and just add this term into hydrodynamics the same way we added this gamma before. Okay, then you can just repeat the calculations, and what you will find is that the conductivity now has a Drude-like peak. So this I omega becomes I omega plus big omega. So big omega again is a supercurrent relaxation rate. I'm using omega to differentiate it from gamma because we're going to have both in the near future. So So this is yet another way to get a Drude peak. Okay, so if you look at the the frequency-dependent connectivity, and you get something like this. Okay, so I told you yes. So what people have, a traditional theorist's first reaction when they see a Drude peak is that, oh well, clearly this width is the single particle lifetime. Okay, so I told you yesterday you shouldn't do this. This could be the momentum relaxation rate. Okay, but now I'm telling you it also could be that you've got a wannabe superconductor, and that actually this width is the superfluid relaxation rate. And in terms of these experiments, this is the natural interpretation. Okay, so hydrodynamics with the superfluid relaxation rate is a natural way to think about these metallic phases. Okay, yes.
Wouldn't you expect rho s to be 0 when you have a finite resistance?
No, this is the whole point. So this is good. So there's a difference between having a condensate and having phase coherence. Okay, so exact. So this phase, there is a condensate, but the phase is disordered by these vortices that can move across the sample over some time scale. So the phase is coherent over some time, but eventually it decays because of the motion of these vortices. So, yeah. Let's do that. Okay, perfect. So that's good. So excellent. So let's follow. So this is fun. I want to go through this. This it turns out it's a nice calculation. So indeed. So last time we said, well, we could add this term to the hydro, but then we did even better and we actually calculated gamma, right, using the memory matrix. So similarly, we should be able to calculate this superfluid relaxation rate from the memory matrix. And to do that, we should find a term that doesn't commute with J phi. Okay? So let's try and do that. Yes?
So you're saying that this omega should always be expected to be non-zero in 2D?
It's non-zero in 2D with a magnetic field or above the Kosterlitz-Dawes temperature, where you need to have some vortices that are moving around.
Okay.
And yeah.
So I was wondering then what happened. I thought that you were talking about the middle phase, but you're saying it applies to both the superfluid and the metal?
No, very good. So, that's a good point, actually. Yeah, indeed. Yeah, so it gets at 0. Very good. So there's some extra levels. Okay. Right. So you have to have vortices. There are vortices, but the vortices have to be mobile. Okay. And so what can happen is that vortices can get pinned if they're impurities. Vortices can get pinned to the impurities, and another thing the vortices can do is form a lattice, and that lattice can get pinned. So there are various things that can happen that even though there are vortices, they can prevent them moving, and that's what happens here. So the vortices need to be able to move across the sample to have this effect. Yeah, thank you.
So why do you assume that the hydrodynamic regime is applicable?
No, right, very good. So very good. Here it's certainly applicable because J phi is conserved. Okay. So as long as you wait long enough, so hydrodynamics is natural without quasi-particles, but even if you have quasi-particles, as long as there's something that lives even longer than the quasi-particles, then you can use hydrodynamics. And here this J phi is infinitely long-lived here. And as long as you're close enough to this transition, this width goes to 0, eventually you'll be in so there's certainly some window here where hydrodynamics is valid. And as you move out in this direction and the width gets broader, eventually it won't be valid anymore. Okay, but close enough to here, this peak will be very narrow, and it will be valid. Okay, so let's try and calculate. I do want to get to charge density waves, so I'll be a little brief, but I just want to give you the essence of how the calculation works. So, okay, so we've got to try to write down a Hamiltonian H prime that we think is not going to commute with this, all right? And so this is in the spirit of effective field theory, so we're sort of going to make it up. Okay, it's not a microscopic Hamiltonian, this is some long wavelength Hamiltonian. And so the natural thing to use is the charge density, because the charge density doesn't commute with phi, right? It has, remember, we had this commutator, phi pi is I delta function, all right? So it's natural to try to write down Hamiltonian that's made out of charge, And so a natural term is this capacitance term, okay, in a Josephson junction language, it would be called a capacitance term, on-site capacitance term, self-charging term, which is rho squared d2x. Okay. We don't want to add rho because rho is just a chemical potential. So the next simplest thing you can write down is rho squared. So let's try this. So if you commute this with J phi using this canonical commutation relation, hopefully it's clear. So you basically move the rho inside, you commute it with this, and the rho squared, you get a rho, but it's inside a derivative. So what you'll find is that J phi dot, which is H prime commutator J phi, is the integral of a space of the derivative of rho. Hopefully that's clear. So you have, there's the rho phi, there's this commutator, and you can just do it. It's one line, okay? Right, because that means that phi with rho squared is rho, okay? But this happens inside the derivative. And this is not good, because this is 0. Because phi is not single valued, because it's a phase, and so you can have a winding that makes this non-zero. But rho, the charge density, is a perfectly single valued function operator, and so if you take its derivative and integrate it over space, you're going to get 0. Okay, so it doesn't quite work. But this is good, because we know that to degrade the phase, we need something topological. There need to be vortices, and we haven't mentioned vortices here, so this cannot have worked. Okay. So how do the vortices work? So the way the vortices work, a slightly low-tech, but I think correct way of saying it is that, so the supercurrent was the integral over all the space of the phase of the Goldstone boson. Okay. But now suppose you have a little vortex here. In the core of the vortex, the symmetry is restored, and the Goldstone boson is not well defined anymore because the symmetry is not broken. So actually, this current is not valued everywhere. It's only, the supercurrent only exists outside torus or R2, outside the cores of any vortices that exist. Right? Because so the supercurrent operator is actually defined, it's not defined inside the vortex because there's no Goldstone boson inside the vortex. Okay? And so this starts to look topological. So if you do this and you redo this calculation, then this grad rho is only over the outside of the cores of the vortex. Right? Because there's just the supercurrent is 0 inside. Because the total derivative is 0, that's minus dx of grad rho inside the cores of the vortices, because the integral over all the space is 0. You can put it on the torus if you're worried about boundary terms. But this is perfect, okay? Because this tells you that J phi, and so basically it's a theory. I mean, we could have put rho to the 20 here. As long as you have a local interactions, okay? Local interactions can only degrade the supercurrent in the presence of vortices, okay? Because otherwise, you always get this total derivative of a gradient, which is 0. Okay. So now, right? Now that we have this, we can use our memory matrix formula to calculate omega. So remember, omega is going to be related to, do I have it more precisely? Well, right. It ended up being related to the sort of the 2-point function. Yesterday it was of p dots, right? So today it's of j phi dots. Right? Yes. Yes.
But in your Josephson relation, right, so you just overlay at some other term, right, so there's phi dot equal minus mu, but there is also the effect due to charging, right, so there will be some extra chemical potential effectively.
Let me see. J phi. No, but this. Sorry, I'm not. So this is just. This is the definition. This is the exact definition of J phi. So I haven't used. There's no Josephson relation here, right? It's just. I'm just using this, and I'm using this commutator.
Right, but then you come once you complete this phi dot, right, so
but there's no phi dots. I mean, there's J. Yeah, I think I know what you're saying, but I think it's okay. So the Josephson relation does not change this commutator. Well, yeah, I think. Good. I think right. Very good. I think probably the way to. I think the way to think about it is that this equation with the extra derivatives. One should think of it more. It's a hydrodynamic equation, and so I think it's more about expectation values than operators. I mean, because the operator equation, this is exact, I think, as an operator equation. So let me think about it some more, but I don't. Yeah, I think it's okay. I think it's exact. Okay, wait. So was this okay? So it's nice. So the way the topology appears is that you're trying to take commutator with something that's a total derivative. And to beat the total derivative, you need to have some boundaries, of non-trivial boundaries where things can happen. And so that's J phi dot is given by something in the core. And then the formulae that we used yesterday essentially say that omega is related to the Green's function of J phi dot, J phi dot. There were some omegas, limit omega goes to 0, imaginary part, so on and so forth. But phi dot is basically this rho localized on the core. So if you follow some steps that are very similar to what we did yesterday, you find that omega is given by the number of vortices times, let me be very schematic, I'm going to be very schematic, okay, that you can look in the paper, times an integral over the cores of each vortex, okay, and then it ends up being related to the low frequency limit of the retarded Green's function of the charge density, and that makes sense because J phi dot has a phi, has a rho in it, and a gradient. So, okay, you know what? I'll write down the precise answer. So omega is the number of vortices, an integral over the cores, double integral over the cores, an integral over k. A k squared, e to the I k x minus y. I'll tell you where all these things come from. Now we lost the, well, J phi dot was the integral over the core of grad rho, right? And so remember that omega was the retarded Green's function of J phi dot. So we use J phi dot is grad rho. The grad gives a k squared because there are two of them. There are two integrals over the core because there are two j's and they're both integrals over cores. And then there's the imaginary part of this Green's function of rho, which is this rho that appears here. And this limit omega goes to 0 we had yesterday. And then this comes from Fourier transforming everything. Okay, so hopefully this is at least a little bit, yes?
X and Y belong to the same core, or are you related?
So there is a contribution from different cores, but I think that's just 0. So they're the same, yeah, same core. Yes. Yes. Yes, 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 yes.
So this is very, it really cares about the normal state. Is there
Well,
a disorder or
absolutely. It cares about whatever the normal state happens to be. Right, so yes, that's right. That's right. And so indeed, so let's, okay, so this is an exact result. So this is the analog for superfluids to the general formula we had yesterday for momentum for gamma, right? I had some general formula. And now we can try to see if we can actually evaluate. We need to know this Green's function. Yes? Very good. Yeah, I think you need a hierarchy of timescales that you probably need them to move more, to move more slowly so that you have a sort of snapshot where there's some hydrodynamics going on with the cores fixed at that instant in time. Yeah, I think. Yeah. Yes.
So can you think about this as just, okay, so I have broken phase, so I have a new conserved quantity superfluid density, and then the way to get break this conservation locally is to some vortex or like some threshold because this also breaks the translation.
No, it doesn't. This is not. Nothing's breaking translations.
Vortex also.
Well, they move around. They can move, so they're not fixed.
So, but okay, then the way to relax this conservation of superfluid density is to put
No, so it's not a. So the superfluid velocity has nothing to do with translation invariance. It only is related to this internal U1 symmetry, and so the role of the vortices. I mean, vortices can crystallize and form lattices and so on, but their role here is to just be able to move across the sample and relax the phase. It's not related to the fact that they're at some fixed position or anything like that. Is that? So maybe I didn't understand the question.
So just general framework kind of. So we now get rid of yeah. So here we just have a new conserved quantity, right? Conserved density, which is superfluid density that comes from like that we assume that there's a broken phase. And this is the way to relax this.
Yes, yes, that's right.
So
But you see, it's a bit different, right? So because this is right. So momentum was a conserved quantity associated to a symmetry, and so that was relaxed by breaking the symmetry weakly. Okay, this is a conserved quantity associated to a sort of topological winding, and so we relax it, which is related to a Goldstone boson, which is related to the fact that the Goldstone boson is a phase. Okay, and then we have to relax that by relaxing the topology, and we do that with these vortices. Okay, but yeah, they're analogous. But the words are a bit different. It's not symmetry breaking symmetry, it's topology breaking the topology. Yeah? Is that? Yeah.
So in magnetic field, the number of cores should
Yes, it goes this thing should go like B or something.
omega
Yeah.
should be in general dependent on the magnetic
Absolutely.
field spread out.
Yes, yes, that's correct. And in fact, that's what you see. So in these experiments, this peak gets bigger as you increase the magnetic field. The width gets bigger as you increase the magnetic field.
And another related question was, so this whole calculation is basically dependent on the fact that J phi is a conserved quantity.
Yes.
Now, your superfluid current, you can, I mean, two things enter, which is basically the gradient of your order parameter. You can have a spatial variation of either your phi or the amplitude of your order parameter. So
Yes, but that's not a ghost. That's a gap. That's a very massive excitation. So that doesn't enter into hydrodynamics.
okay, so it's only the low energy part.
It's only the phase that is low energy. In general, if you tune close to TC to some phase transition, it might become light. But we're deep. This is deep in the ordered phase, and so the amplitude mode is gapped. Yeah, so it's just one other non-hydrodynamic mode.
What's in front of the info? Is it the total number of vortices?
Ah,
What
thank you.
is that?
No, indeed, this is the total number counted without signs. So the vorticities. Yes, that's right. Yes, this is not. This is
The bigger sample I get, the more like the relaxation I
no. So this is a density. Sorry, this is a density,
get.
but
without
without
the
signs.
sign.
Yes, it's not the vorticity. It's just the total number of vortices.
So G rho rho is supposed to calculate the momentum.
In the whatever's in the core of the vortex. Yes.
And there's some assumption that the coherence length.
Well, not yet. Well, okay. So that's right. So this sort of sharp boundary that I mean, I think one could do a more sophisticated modeling of, but this like basically that the superfluid, the J phi is 0 inside and non-zero outside is in some limit where, indeed, that there's no crossover. It's just yeah.
But you also need the core to be big.
Well, not yet. Not so. Apart from this assumption that I just said, not now. Well, let me come to this right now. Okay. So this is, I think, this could be a microscopic vortex. Okay, as long as the crossover is fast. As long as. But now let's try to calculate this. So a very nice limit is when the vortices are large compared to some microscopic scale. Okay, because in that limit, it turns out we're looking at the low frequency limit of this rho 2-point function. And if the vortices are big, we can use hydrodynamics of the normal phase to evaluate this rho. So that you can only do where the vortices are big enough. And so this diffuses, well, if translations are broken, this would be diffusive. And so you can actually use the hydrodynamic form of the normal states in the core of the vortex to evaluate this, okay? And if you do that, the answer you get, when you do all these integrals, you get that omega goes like the number of vortices. It goes like the area, the size of the vortex, okay? That's because there are two integrals over x, but only one over k, so you're left with one integral over x, the size of the core, divided by the conductivity of the normal state, okay? And that's because this rho has the conductivity of the normal state in it. And so this is what you get. And so actually, it was one of these sort of bittersweet moments. This is an old formula. This is from the 50s and the 60s. So Bardeen and Stephen actually derived this formula in a very, very different method. Okay, so they imagined the vortex as a very classical picture. We have a vortex, and they have you have a supercurrent, and then there's a sort of a Magnus force. It's like a soccer ball in the wind that it bends. Okay, if we have a vortex in a superfluid, there's a force that acts on the vortex. The superfluid pushes the vortex up. That does some work, and you can work out how much heat you generate. Okay, they did this calculation in the 60s. We get the same formula on the nose with all the 2's and pi's and everything. But this is a much more, well, here the domain of validity of the calculation is clearer because we have a more general formula, and you take the limit where the vortices are large, and you can get this out. Okay, just 2 seconds, and I'll. So hopefully this is very normal. This is very reasonable that the normal state conductivity should appear, because if the vortex is getting pushed up, and as the vortex moves, the normal state matter inside the vortex also moves, and so there's a current of the normal state, and that creates some heat. And this normal state and how much heat it generates depends on the normal state conductivity. Okay, so so if you can think of the motion of the vortex is like having some uncondensed electrons and moving them around, right? So to relax the phase, we have to move the vortices across the sample. How easy is it to do that? Well, that depends on the conductivity of the stuff inside the vortex, right? So that's why this normal state conductivity appears. Yeah.
It would seem though that at least on a formula level, once you increase the core size of the vortices, then you can't assume that either rho or v are zero, and you can't just ignore them and they can put you to the relation. Not the superconducting density, but the normal density and velocity, right? Because
No, that's
to superconducting, you have to go to a finite density.
so the normal. No, so let's just say that the thing's very disordered, and then so momentum is just not the easiest limit to work in. You can combine them both, and then actually you have an interplay between the momentum and J phi. But if just go to some limit where it's very disordered, then there's no momentum, and you can just forget about the velocities. That's the easiest limit to work in, which is probably relevant in these films. Which
So
are
you want to have a disordered system and then raise the temperature, increase your core size.
yes, correct. Yeah, exactly. Thank you. Yes.
The higher magnetic field is Anderson book.
Yeah, well, right, but it's good, very good. What happens? No, right. Eventually, actually, how do you think about this? Yeah, no. Eventually, the condensate disappears. Right.
So, but I expect sigma n to be zero. If I just have the normal state.
Yeah. This is that's right. So this yeah, that's a bit yeah. So let's be at some non-zero temperature, and so right. Sorry. So good. Yeah. So what you actually see in this is so the way you see these superfluid insulator transitions is you plot the resistance as a function of temperature. Okay, and so you cool it down, and in the superfluid state it goes to 0, but it doesn't go to 0 until you actually get to 0 temperature. So it looks something like this, and in the insulating state it goes like it's finite over most of the range, and then here in this metallic bit in the middle it looks something like this. So again, yeah, probably we're not really at strictly 0 temperature. yeah, this is not what you want to use at 0 temperature. But at some finite temperature, there'll be some finite resistivity here. I just want to mention, yeah, I'm not going to do anything about it, but so remember I said, but I want to mention because it might connect with things that, other things that are going to appear in this workshop, sorry, in this school. So I said that if you wanted to relax grad phi with a local interaction, you need to have vortices, okay? But another option is that this H prime, okay, could be a non-local interaction, okay? Now, a non-local interaction sort of has inverse gradients, if you like, and these inverse gradients can beat this gradient, all right? And it turns out that a very nice case of a non-local interaction is one you get from a Chern-Simons term. And so actually, if you take a superconductor and couple it to a Chern-Simons term in the right way, and then integrate out the Chern-Simons term, it generates a non-local interaction. And that non-local interaction can have has a non-zero commutator with this J phi. Okay, so you can read about it in the paper, but Chern-Simons plus superconductivity has some non-trivial vortex dynamics. Okay, I'll just leave it at that. Sorry? Not that I know of. But I don't think it's impossible, as you're going to hear from the other talks. Chern-Simons terms exist, superfluidity exists. It doesn't seem like it should be impossible for them both to. But I don't know one that has quite the right coupling. So okay, I guess I walked into this. Okay, so I'll just write down if you have, it turns out if you have J, so Lagrangian L, and there's some L0, and this is Lagrangian that if it were left to its own devices would become superconducting. Okay, that's this thing. Then you add, then this Lagrangian has some electric current J, and this current J can couple to an external electromagnetic field. All right, so this would be what you normally have. But now imagine coupling it to some dynamical field that has a Chern-Simons term. Okay. Now, if you integrate out this Chern-Simons term, you'll generate a non-local interaction between the currents. It's called a hedgehog or hedgehog, yeah, something like that. You generate. So if you generate something that's this, I think it's J mu, epsilon mu nu rho d nu J rho over del squared. Okay. This is a well-known thing from quantum Hall. If you integrate out, but now it's not quantum Hall because there's also this sector that wants to become superfluid. If you take this interaction, this includes a term where this one is zero, where this is zero, so that's the charge. This includes a term that is charge times 0, 1, 2, so the curl of the current divided by del squared. And you take a non-relativistic limit where the omega squared is not important. This is just k squared. It's like an instantaneous. So this is like a sort of a Coulomb interaction, but it's between rho and the curl of J. All right. It turns out that this interaction doesn't commute with this, and it can degrade it. Okay. So, but I don't know a physical realization of this. Okay. So I just wanted to mention that Chern-Simons terms generate non-local interactions that can disorder the phase of a superconductor. Okay. Another way of thinking about it is by flux attachment. Okay. So if you have a Chern-Simons term, let me get this right. Let me see if I can say all the words. Right. If you have a Chern-Simons terms, the density rho, the charge density, gets Chern-Simons flux, magnetic flux attached to it. Okay, and then but this Chern-Simons flux also couples to the current, which is going to include a supercurrent. And so when you try to create a current, you move the electrons, but these now come attached with these move Chern-Simons flux, and that's like a motion of vortices, and that degrades the supercurrent. Okay, so essentially the physics is that the flux attachment creates vortices, and the motion of those vortices destroy the superfluid. Yes. Yes. No.
Sure. So Or is it, I mean, do I need this short times? Or if I had any way of long range injectors, which I don't know, that's the
Yeah, so any, well, it's, let me just say it's delicate, because I want to say one more, let me say one more unrelated thing before I finish, and let me talk about it later. So I'll just say long-range interactions can easily disorder the phase of the can easily disorder the phase of a condensate. That's what I'm saying. Without, yeah, okay. Yes.
What happens if you vary the coefficient of the transition?
Yeah. Okay. Well, it appears. Okay. Yeah. This sort of, unfortunately, this is sort of the tip of an iceberg, but a small iceberg, but nonetheless an iceberg. So it ends up. There's this almost. I mean, it ends up. Yeah. Okay. I probably shouldn't have mentioned this, but right. I mean, this rate omega that you calculate is going to be proportional to either this coefficient or 1 over this coefficient. I don't quite remember, but it will enter in all various places.
Is it just a smooth behavior, or there's some dramatic things?
I think it.
Certain values.
No, I mean, yes, right. So in certain setups, it probably should be quantized, but I think as far as the hydrodynamics is concerned, it's smooth. Yes, it's smooth. Yes, yes. Yes, it's smooth. So I did start 5 minutes late, so I'm also just going to say, what was it, 10 minutes? I just, now that we've set up, so okay, but the main thing is you can look at Goldstone bosons and you can use the memory matrix formalism to discuss the relaxation of Goldstone bosons due to topological effects. Okay, that's the nice thing. And so in hopefully 5 minutes, I just want to say one thing about the charge density wave case, because it's interesting. It's a little bit interesting. So we've already done almost everything we need. But because I'm not going to say very much, you can all look at this paper from earlier this month. And so this is with Luca and with Anna, who are here. And so let me just say, so here, so just now we talked about the internal symmetry, but you can also spontaneously break spatial symmetry just by creating a wave. Now, spatial symmetry is more complicated because there are all kinds of different patterns you can have in 2 dimensions. So just for simplicity, let's just talk about the case where there's just a wave in one direction. Okay? And so we imagine that the charge density has some profile Qx. That's the condensate. And the Goldstone mode is now the fact that you can slide this condensate. And so we can add, if you like, a phi of x here. Okay. So clearly the Goldstone modes are these translations. So we have to include this. And so now, remember before, in the U1 case, it was charge that generated the translations. Mu, the chemical potential, is the source for the charge, and the Josephson relation was phi dot is minus mu. Okay. Now it's translations that are broken. Translations are generated by momentum, pi. The conjugate to momentum is the velocity, right? It's the source for momentum, and so you should expect that the Josephson relation for this phase is that phi dot is the velocity. Hopefully that's plausible. Okay, you can get it from the commutators and so on. So with the charge density wave, the phase, time variations of the phase get related to the velocity rather than the chemical potential. Okay, yeah. So now you do exactly the same thing. You just take this extra Josephson relation, you add it to the free energy, and you grind through the rather short at this point once you're used to it, hydrodynamic calculations. And so what you get, so I'm just going to give you the answer. Oh, I'm sorry. Well, actually, you still get a delta function. Okay, this is like it's still divergent. Okay. Now let's try. So the most new thing that happens here is what if we break translations a little bit? Okay, so here we spontaneously broke translations. But what if, on top of spontaneously breaking it, like it wants to spontaneously break, but then we explicitly also break translations a little bit. So then you have what's called a pseudo-Goldstone boson, right? So you're breaking an approximate symmetry, all right? And this is well defined as long as you only slightly break the symmetry. And so what happens is that you get a mass. Okay, so if we break translations, there are now, in a symmetry broken phase, there are now two effects. Momentum relaxes like it did before, so pi dot will have some minus gamma pi, all right? But also, in the free energy, the phase gets a mass because it's not a Goldstone, it's not quite a Goldstone boson anymore. Okay. And so now you take these two terms, you grind through the hydrodynamics, and you can calculate the conductivity. And something new happens because of this mass. What you get is sigma 0, and then you get, I'll write it down. Essentially the mass. Okay. All right, so what is this? So first, let's turn off the mass, so there's no, forget about the Goldstone boson. Then these omegas would cancel. And this is the Drude peak that we had before, right? Just due to relaxing momentum, okay? But now it gets this extra more complicated structure because of the mass. And so if you plot this function, what's happened is the mass has moved the Drude peak away from zero frequency, right? So before we had something like this, where we broadened momentum relaxation, broadened the Drude peak, but it didn't shift it. But once you have a pseudo-Goldstone boson, the peak actually shifts away from zero, and so the width still depends on the momentum relaxation rate, but its position is essentially given by the mass of the Goldstone boson. Okay? And in fact, if this sigma 0 were 0, which for example in the Galilean invariant system it is, this would actually be an insulator because the conductivity would be 0. If you put omega equals 0 here, this is 0. And this is something many of you may know, for example, that a Wigner crystal is an insulator. Okay? So if you spontaneously form a crystal, something that breaks translations, all you need is the tiniest bit of disorder, and it's pinned. It can't move. It doesn't move. It can't slide anymore. Okay, and that's this effect that the DC conductivity is 0. Okay. However, there's still this huge peak at finite frequency, which is the gapped momentum mode. Right. So a very new thing with spontaneously broken space-time symmetries is that if you explicitly break the symmetry a little bit, you get this peak moves away from zero frequency. Okay? This has also been known for a long time. Right. Okay. Very good. Yes. But now, because there's because the disorder tends to be relevant, this peak tends to get pushed to UV scales. Unless you have some other reason that it doesn't, because disorder tends to be irrelevant. It tends to be a relevant effect because of this random field term. But yes, there would be a peak, but it typically gets pushed out of the hydro regime. Okay, I want to say one more. Yeah, I'm good. One more thing. But now we can also complicate life by this is momentum, but what about the vortices? Okay, so this is also a phase. All right. And so just like for the superfluid, we can also relax the phase, right? And so what's a vortex in a charge density wave? It's a dislocation. Okay. If you told me as an undergrad that I'd ever give a talk using the word dislocation, I probably wouldn't have believed you. But okay, it's actually it's a nice thing. It's a topological defect in hydrodynamics. Okay. So dislocation, I mean, it's a very mundane thing that you worry about in crystals, right? So here's your crystal. This is the phase varying. This is this cosine. And the dislocation is when one of these, it ends. And so you have something like, these are lines of constant phase. Plot the charge density, so it's oscillating. And then on top of the oscillations, these are the oscillations of the phase. You have the Goldstone boson, and a vortex, a winding of the Goldstone boson appears as a dislocation like this, okay? And so in the same way, right, and so but dislocation, okay. So what causes flow? So before we applied an electric field, and that made the vortices move across the sample. The natural thing that makes a dislocation move is pressure, because it's related to momentum. It's related to translations, right? So if you apply a source for momentum, that's like a pressure. So if you strain these things, these dislocations will start to move across the sample. Okay, and in fact, melting the BKT transition is this proliferation of dislocations. Okay, it disorders the phase. So okay, anyway, you can put this in the hydro as well, and so this means that the phi dot, which was, remember I said it was Vx, now it has a minus omega phi. And so now we have, life gets complicated, so there's a momentum relaxation rate, there's a mass for the pseudo-Goldstone boson, and there's the proliferation of dislocation rates, the rate at which the phase degrades. Okay, these are all three different effects, right? You can put them all in, and this width ends up being depending on both of these, for example. All right, so let me just end. So the reason we wrote most of what I said was essentially known in the 70s about this structure. The reason we wrote the paper is that it turns out, so what's very interesting about this structure, okay, first you should know that a lot of unconventional metals have charge density wave phases, so the cuprates have a lot of excitement in the last 5 years about charge density waves. And a mystery that if I'd had this extra lecture in between lecture 3 that got missed, what I would have told you about is that one of the mysteries of the cuprates and other so-called bad metals is that the conductivity is very small. Okay, they conduct, but the conductivity is very small. And that's very confusing because strong coupling, I'm saying, might favor this hydrodynamic regime. Okay, but hydrodynamics leads to a large conductivity, especially if you have this momentum that's conserved. All right? But here what's very nice, what happens if you have a CDW, a charge density wave, is that it moves the peak away from zero. Okay, so you can still have it. So remember before we had that the conductivity went like 1 over omega. Okay, sorry, 1 over gamma. So if translations were weakly broken, the conductivity was necessarily very large. All right, but here, yeah, there's all kinds of things that haven't. If you put omega to 0, the conductivity is just a sigma 0. It's completely divorced from the momentum relaxation rates. Okay, so you have this huge sharp peak, but it doesn't determine the DC conductivity. So the nice thing about charge density wave physics is that it decouples the momentum relaxation rate from the DC conductivity. And in fact, if you look in many bad metals, you see that they do have peaks at finite, that they don't have Drude peaks. Actually, they have. It's not as impressive as this. They look like this, but in many of these exotic metals, you can actually see peaks away from zero frequency, and so it may be that this kind of hydrodynamics is the right framework to think about these peaks.
Can you explain it in any other way?
I don't think so. Well, the other thing that can give you peaks away from zero are cyclotron. So if you break time reversal, you can move the Drude peak. But these things, and time reversal is not broken in these phases. So indeed, yeah. So our argument in this paper is that momentum relaxation can broaden a Drude peak. But if you want to move it away from zero, you have to spontaneously break the symmetry as well, the space-time symmetry. I don't know any other way to do it. Yeah, let's stop now.